So here is a theorem which we will now prove. We have a function v, the constraints g, the manifold. I forgot one important point. Here. Regular. Almost forgot it. Now x has to be a regular point. Well, now by continuity, let me remark it by continuity, the regularity extends from x0 to a neighborhood of it. Why? Because regularity means the full rank. And if you have a matrix which continuously depends on some parameters, and on the one point it has a full rank, then this should extend to a neighborhood. Just like the invertibility of a matrix extends to a neighborhood. It's the same thing. Proof. Now we have to take some tools. We need a parameterization. For which we know to exist if the manifold is regular. Such that P0 is equal to x0. Now this is taken from omega 1, the subset of R m minus s. M minus s is the number, we call it number of degrees of freedom. That's the real dimension of our manifold, is m minus s. And this is mapped with all properties we have asked for a parameterization onto the neighborhood of x0 on M. Now, alpha into V of P of alpha is now a standard function of M minus S variables. And it should have a minimum there at 0. We now switch in the standard theory, which says that the gradient of this function should vanish. That means d alpha j of V of P of alpha, alpha is equal to 0. That must be 0. But this can be computed now. This is by the chain rule for derivatives. Sum over I dv over dxi taken at x0 times dp over d alpha j taken at 0 is equal to 0. The conditions for the chain rule are fulfilled. Everything is smooth. But now, by regularity, those vectors, you see P is a vector. P of alpha is a vector in big space. So we have now you have now m minus s vectors. And they are linearly independent, as is asked by a parameterization to have. Parameterization also has a full rank. So those vectors not only linearly independent, but they are a basis of dx0. They span it, and they're linearly independent. They're the basis. Well, that means d v 0 is equal to sum lambda I d g I. Because this is orthogonal to the tangent space. Yes, this is orthogonal to the tangent space, this one. Yes. And we know that the matrix D2 or D alpha J D alpha K of V P of alpha and taken that alpha is equal to 0, this matrix should be positive semi-definite. That's again the general theory. A function of m minus s variables has a minimum. But now you have to compute this. Is equal to d over d alpha, excuse me, I changed the index here. Instead of k, I have a L here. Okay? And there's the first derivative first. xy d py over d alpha j. And now we differentiate once more. It's a bit a clumsy formula, but we have to do it. That is the sum over I and k. You have now one sum more here. d2 over d xy d xk dp I d alpha j dp k over d alpha L. That comes from differentiating this factor. And this is now taken over. But now we have to differentiate this one. Plus sum over I dv dx I d2 di over d alpha L d alpha j. Well, that's the full formula. I didn't write it completely. This has to be taken at x0. And this has to be taken at alpha is 0. It's the short writing. Look here. That's the way how you should write it down. First the derivative and then put the points where you just according to the chain rule. Now, but taken as x equals to x0, we should now get rid of this. Pi. You see, it's a very short writing way. This v is not just any point, but it is the point where the parameter is. That should be 0. I think I've made some, not mistake, but something let me. I took here this to be 0, but that's not 0 because dvxy. That's what we have here. Oh. Yes. Yes. This here is equal to I should take this into account. Well, yes. That's the. That was the mistake. You should take the second derivative, not of v, but of the whole Lagrangian. That was my mistake. Please correct this here. Here and here. That's the Lagrangian. Yes. 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 So we have now to put this here. dv dv, okay. So this is what in fact we yes, second derivative. That's again. Here.
dv or dl?
Pardon me?
Above that, is it dv or dl? This part? Or
No, this is dv.
okay.
Because it is just this condition here. Yes. So that's okay. Yes.
Yeah,
No. It's minus.
Yeah.
It's minus. Fine. Thank you. Well, yes. So now you can. That's what we have, but that's only for v. And we have now to to take the derivative of the other one. Alpha j, alpha l of what? Of some lambda I gi. Again, yes, now it's correct. L is here, L is here. That's okay. Yes, okay. No. Yes. We have to take the second, okay, the minimum. Yes. And this is equal this is equal to what? This is equal to this one. I will just write it up, and this is equal to minus sum over I, and this should be now computed from this formula. That means that dv over dxi is equal to minus lambda sum over, well, I'm lacking so much indices. I have an I already here. So, okay, dj, dg, k, or d, there, e, x, y. You have to put it here. So, minus I, and then comes lambda k. So, I, lambda k, d, g, k, d, x, y. That's what it is. Yes. And now, sort of recognize this as the second derivative of the full function of the Lagrangian. And we have it in fact here. Okay. I'm sorry I overlooked something in the proof. The second derivative must be here too. Okay. Yes. That's I here. And here's the second derivative. I think I will stop here. I made a serious mistake. I will remind you for next time. I apologize for that. I made a technical mistake somewhere here. And somewhere the second derivative for g also should come in. And I don't see in the moment how. d2L has not only the second derivative of v, but also the second derivative of g, which I don't see here. The whole thing is not complicated, but yes. Okay. Otherwise we will lose too much time. So this part here is trivial, and this here positive semi-definite. Now, here the v should stay, because we asked the local minimum. And this means the local minimum of in variables of alpha. Then it concerns only v. And you should conclude that this is a positive semi-definiteness of the whole L. That's what you have to conclude. And we start with that here. That's okay. We know that this is positive semi-definite, and we should conclude that this is positive semi-definite only on the tangent subspace. That's what we have to do. It's a simple geometry, but somehow, yes. Okay, that's this here, and that's this here. You should, yes. Well, I should remind you for next time. It's better. So, I suppose now you acknowledge that the theorem is correct. And we will now go over to the most serious application of this, and that's the catenary. Okay. So this now is supposed to be true. Oh, that's not needed. I don't think that we need the whole statement of the theorem. We know it by heart. The gradient of the Lagrange function should be 0, and at the solution, at the stationary point, this should be positive semi-definite, and in order to check the local minimum, you have to check the positive definiteness of this matrix here. The catenary is the really non-trivial application of this, so I will go in some detail in this example, just to work it out. Catenary. You have chords of lengths d1, d2, and so on. The points have the coordinates 1, 2, and so on. And this is some L, the length, where you have the distance between the points where the catenary is hanging. And we have already defined the manifold before. I will just recall. The manifold is given by M, well, the set, not the manifold, by the condition xy minus xy minus 1 square plus yi minus yi minus 1 square minus di square equals to 0. I goes from 1 to n. No, n plus 1. You have n points and n plus 1 chords. That's the definition of the manifold. Now, and we proved that the set of singular points, if it is not void, is equal to points x, I, y, I, let me say it, hat, such that yi hat is equal all to 0, and x, y hat x, y minus 1 hat minus x I minus 1 hat equal to epsilon I di. Epsilon I is from the set minus 1, 1. So this is the catenary which completely stays in the x-axis, and its chains just go this way. And this is only possible if some epsilon I di is equal to L. Only in this case we have some non-trivial singular points. Otherwise, that's a fine manifold. But if you take this set of singulars out of it, and then you get the standard manifold, on which we will now consider the whole matter. Now we come to a very subtle decision. We have considered our catenary to be in the plane, xy plane. And this is the gravity. You can understand this catenary much better if you consider another one. The other one is the catenary which can move not only in the plane, but in the whole space. So you will consider this set xy minus xy minus 1 epsilon I plus z1 zi minus well, of course, you expect that the catenary, even if it can move in the space, when it comes to equilibrium, it will be in the plane. That's somehow that's obvious or plausible. That's of course also true. But the question is now, how about singularities? If you do the same consideration as I did before for the plane catenary and looking for non-singular points in it, then the same consideration will give you the same set. You will see that singular points all lie in the xy plane. That's the first. That's the only additional conclusion you will get from this consideration. So it's the same set as here, only now embedded in a larger space. So now you have your M embedded in R 3n. And you have the same number of conditions. So the degrees of freedom, as we say, will be 3n minus n plus 1. The number of constraints remains the same. And we get 2n minus 1. So, for example, if you take something like that, the most, well, not the most simple, but this one. In the plane, you have 2n minus n plus 1. Then you get n minus 1. So this means that the set of which this is moving is a curve. It has only one degree of freedom. And you have just one point. Then in 2 dimensions, the dimension of this manifold is 0. It's fixed, but not in 3. It can move in the z direction, the xy, and people sometimes show this as z direction coming out. So, you see, and another curiosity, which kind of curve is this? It is something like that. You can map this curve in the plane, of course. But this mapping does not determine the shape of the curve, only topologically. And if you have the singular case, then this curve will be something like that. It's just interesting to play with it. The catenary is a beautiful example where you can play, you can build a catenary with some threads, and you can move in a very high dimensional space by just making experiments with your fingers. A very rare case where you can do that. That's why this example is so fine. If you have 3 of them, well, then in the plane you will have a surface. This would be a surface, a 2-dimensional surface in a 3-dimensional space. That will be your manifold in case 3 points. If you have the z direction too, then the dimension is even higher. Okay. Good. That much. So. Now, first result is that the function m, our function v, is equal to, well, the potential energy in the gravity. I is equal to 1 to n y I m I g. The potential energy of each particle is its height. It's a very simple function, linear. But which is non-linear are the constraints. So we say we claim minimum is taken in n. Minimum cannot be taken in a singular or on singular points if they exist. That's the first claim. Why? First of all, the whole M is compact. That's trivial. It is bounded, and it consists of zeros of a continuous function. So it is bounded and closed. You see, the points cannot. Don't forget that. These are the fixed points here. So taking these together, you see that the set of all points satisfying this is bounded and it's closed, so it's compact. So the function takes its minimum there. But the minimum cannot be taken at S. Why? Because we certainly have a certain configuration which lies below. And then V is negative there. But on S, all y's are equals to 0. It is just so the potential energy on the singular set is 0, and down there it's negative. So the minimum cannot be taken on the set of singular points. And we have now n, which consists of regular points as we have shown. So the minimum is there. And we can form our Lagrangian. That is, L is equal to V plus some I equals to 1 to the n plus 1 lambda I gi. That means V sum I is equal to 1 to n mi g yi plus y to the n plus 1 lambda I. Well, now xy minus xy minus 1 squared plus yi minus y minus 1 squared zi minus z1 minus I squared minus di squared. So, now I will rewrite this formula in a more compact way using vectors and matrices. And I need some space for auxiliary computations here. See, I'll now take the sum of all x contributions here. So this is lambda 1 x1 squared plus y1 squared plus lambda 2 x2 minus x1 squared, yes, plus lambda 3 and so on, plus lambda n yes lambda n plus lambda n plus 1 xn squared. That's the nth contribution, but there is one more, plus lambda n plus 1 L squared minus 2L xn. You see, when you take the last term of this inequality, then you will have here xn plus 1 and xn plus 1 is equal to L. So there is some rest. You will have here x n L minus xn square minus xn. And this is L square minus 2L xn plus xn yes, minus xn squared. And this cancels, so that's the rest. That's the rest term. Now, so you have to have a very sharp sight to see what it is. Well, this is equal to lambda 1 plus lambda 2 times x1 squared minus 2 lambda 2 x1 x2 plus lambda 2 plus lambda 3 x2 squared, and so on. And you end up with plus lambda n plus lambda n minus 1 xn minus 1 square minus 2 L lambda n xn minus 1 xn plus lambda n plus lambda n plus 1 xn square plus some rest, and it is ln plus 1 L square minus 2 xn L plus some constant c, which is the sum of all squares which come up. That is c is equal to lambda n plus 1 sum dE square, which will disappear when we differentiate. It's a constant. But now, this here can be written down very nicely in a matrix form. This is equal to xt lambda x plus lambda n plus 1 L square minus 2L x n plus c, where lambda is a matrix. Three diagonal matrix is that. This matrix is a typical object arising in any kinds of interactions which are one-dimensional, and the parts of the object interact only with their nearest neighbors. You would see it with electrical chains, with heat equation, wherever you interact with your neighbor in the first order. If you have, for example, the the theory of stiffness, then your differential equation is a fourth order, so you have a 5-dimensional matrix. But this is the simplest way, the simplest model of interacting with the nearest neighbor. So the same with y and z. So, or L is now equal to yes. L is equal to 2 mu transpose y plus x transpose lambda x plus y transpose lambda y plus z transpose lambda z, and plus the rest. There is some rest. Lambda n plus 1 L square minus 2L xn, where mu is now just a short way of writing 1/2 m1 gy1 to m n gyn. It's a scalar product now. This. You see what is a fine thing about this function? Once lambda is fixed, then this is a quadratic function of the variables. It's linear and it's quadratic. This is, of course, a very special feature. Can I hope that you will keep awake without the pause, without the break till the end? Okay. When the old professor can, then the young students can too. Okay. So what is now your DL? Well, this is dxl, dyl, and dzl. You have to make a vector out of those vectors. So it has the length of 3n down there. I will not make a break because I will not repose in the break. I will just think on my mistake. So it's better to go back, to go further. Okay. Yes. But now it's easy to compute the gradients. It's quite easy. Well, we don't need this anymore. Okay. Wow. So to compute the gradient, that means set this 3 to 0. Well, but the derivatives of this function, of quadratic function, is linear. That's trivial. So the derivative of this is just 2 lambda x. And so on. So we obtain lambda x equals to, well, what? What is the rest? Well, here you have only the last component, which is derivative. All other derivatives are 0. If you differentiate it with x1, x2, x3, all zeros, only the last one stays. So this is then equal to lambda n plus 1 L times 0, 0, 1. Yes. This part vanishes. This is a constant. So the only which depends on axis is this, and this only the last one. So minus on the other side gives plus. Then lambda y, that's easy. That's equal to minus mu. And lambda z is equal to 0. These are now the equations of Lagrange. this determines the stationary point. There must be one, we know, and it is regular, so there is a solution to this equation. That's trivial, but we have to look how this solution looks out. Now I will introduce the new variables which you would probably remember from the analysis of the regularity. We will take x, y be equal to xy, xy minus xy minus 1, and so on. Y equals to 1 to n plus 1. But now those xi, I, eta I, and zi have also some conditions. That means that the sum of xi is equal to L. That's the last component of the last that's the sum of the displacements in the x-day. And the other ones, some eta y is 0 and zeta y is 0. That's what stays here. Now, I don't need now this. Yes, this can be taken away now. See, we are still now working in the three-dimensional space. But it soon will be seen that we can reduce it to 2 dimensions as well. So there is a lemma. It says, if we have a stationary point, implies first, at most, one of lambda I vanishes. Second, if some of them vanishes, then Ci is equal to L, and all other Cj are 0. Three, if all lambda I different from 0, then are xi I different from 0. And 4, all zi are 0. Zeta I, excuse me, zeta I, yes. Well, this now shows that in fact we will have to do with a plane catenary in the equilibrium position. It must be plane. Well, this one means just a very special case. It is not quite an exception. This is catenary which looks like that. This is a possible case. Then, in this case, you will have, you see, those lambdas, which we call Lagrange multipliers. usually don't have physical meaning, but here they have it, and we'll see it. It is the forces. Lambda is the size of the force in a thread, in a cord. And here, this force is equal to 0. There is there is no need to connect them. They are free. Okay. So, let's look for the proof. Now, the first statement is quite easy because you see when you write down this with these abbreviations, then those equations look as follows. Lambda I plus 1 psi I plus 1 equals to lambda I psi I. Then lambda I plus 1 eta I plus 1 equals to lambda I eta I plus mu I. And lambda I plus 1 zeta I plus 1 equals to lambda I zeta I. That's these equations. Yes. Taken together with those. What we have done here, we have completely changed the variables. We have written down this system in an equivalent way. Now, let's look at one. So if lambda I is 0 or some I. Now look, this here means that that those quantities here are strictly increasing with I, because all mu I are positive. So that's the way how the chain is hanging. That's what it is here. But no, so if this is 0 for some of them, then all of them vanish, because that's the neighbor one. So all of them are 0. Except for or I. So we have this sum here now consists of only one term. So we have then xi is equal to L. That's here, and all other are 0. And then yes, that's what it is. Yes. the second one, well, the first one was trivial because of the strict increasing of this sequence. And that what I have proved here is just the second statement. Yes. Now 3. If all of them are different from 0, then yes, if you would have some psi to be 0, and all lambdas are different from 0, well, then you will have that all of them vanish, which is contradiction to this one. So this proves 3, 2. And now come the last one. The z's must be 0. So we here distinguish two cases. First case, all lambda I different from 0. Well, then we have from here, I did, yes. Then we have psi I is equal to lambda I psi I over plus 1. Excuse me, lambda I plus 1 psi I plus 1 over lambda I. But this is constant in I. So I can call it C1. So summing up gives L is equal to C1 sum 1 over lambda I equals to 1 plus n plus 1. But now, from here, you can also write down Zi is equal to Zi plus 1 lambda I plus 1 over lambda I. And this is again a constant. C2 over lambda I. But now the sum of them is equal to 0. And this constant is not 0. So we get sum of Zj is equal to minus, equal to C2 times sum over 1 over the j. Yes. And this is non-zero. this is non-zero because of this. And this is, this means that this C2 should be also 0. Otherwise it's contradiction. So on all Zi are 0. That is in the stationary point, the catenary is plane. Plane. So one could say, why bother about the third dimension when we know that all stationary points are in the plane? Why introduce the second one? Now comes the answer. The answer comes from the next theorem. Well, I will just take this lambda should stay because I need it. Theorem. At any stationary point, the matrix lambda is positive definite. Positive definite. And any any minimum is strict. So it is almost everything. We know there is at least one minimum, one minimizer, and we now state that this minimizer is a strict one. That's the second information. And of course, the positive definiteness of the matrix lambda is an important statement. So we have to prove to find the matrix of second derivatives of what? Well, of L. And dl was, I recall, dxl, dyl, dzl. Huh? And now I have to make the differentiate once more over all such variables, and you will get this. That's quite clear. Because the mixed derivatives vanish. So, yes. And these second derivatives are just the matrix lambda 3 times. So d2L is equal to lambda, lambda, lambda. And we now have to conclude that this matrix lambda and then the whole matrix is positive definite. It's trivial. If each of them is positive definite and vice versa. But now what we know, that this um, 2L, now it is constant. It doesn't depend on the place where you take it. There is no x, y, z here. It's constant. So d2L should be computed, should be multiplied by, let me call it dx1, dx2, dx3, and here's dx1, dx2, dx3. Well, transpose, transpose, transpose. This is a 3n vector. And this should be positive semi-definite, that means greater or equal to 0, where? On the tangent space. That's not the detail. The tangent space. And the tangent space is given by, we have to derivative, we have to, where are those g's? You have to differentiate first with respect to x variables, then to the y variables, and then to the z variables. And this is equal to 2 psi y d x psi 1 dx 1 minus b yes dx 2 I have somewhere made this. Yes. Okay. I have to differentiate, not write anything by heart. So what can we do there? But that's not needed anymore. dg1 or dx j is equal to 2 should write it down somewhere. Xj minus x minus 1 square plus and so minus dj square equals to 0. And this has to be differentiated. Yes, so that's equals to 2x x 1 yes plus 2 x 2 minus x1 and so on 2 x n minus 1 minus x n minus 2 plus you have to differentiate the last one, and the last one has L minus xn squared, and this is minus minus 2 2 L minus xn. That's what it is. And so on. So you can write it down as the G1 or dxj is equal to 2 psi 1 plus 2 psi 2 plus 2 x n plus 1. It's more symmetric that way. Now we know how the matrix looks like. It has 2, 1, 2, n plus 1. No. This is 2 psi 1, 2 minus 2 psi 2, 2 psi 2 minus 2 psi 3, and so on. Minus 2 xn plus 1, and here is xn. This matrix has one more column. It has n plus 1 columns and n rows. That's what it is. And now you should add the y and z derivatives. It has 3 blocks. Well, so now you have to write down the vector from the tangent space. It should be orthogonal to this, to all this. That means a vector dx and so on to dzn, 3 n components should be orthogonal. That means 2 psi I dxi minus dxi minus 1 plus 2 eta I dy minus dy minus 1 plus 2 xi zeta I, excuse me, dzi minus dzi minus 1 is equal to 0. I is equal to 1 to n plus 1. Now, if you take all zetas to be equal to 0, and we can take all dx's and dy's to be 0, then this means yes, this means that this is satisfied by arbitrary dx, dy, dz. Especially if we take dx's and dy's to be 0. But then our form dl dx dy dz is equal just to lambda, which is positive semi-definite by supposition for arbitrary dc. That means that the matrix lambda is positive definite itself. This conclusion couldn't be possible if we would work only in the plane. There would be no z freedom. So we satisfy this tangential condition easily on a special set of points. And there we see that this is positive. Why could we take z equals to 0? Why? Because at any stationary point, zi are 0. So that's justified. This is just it. So lambda is positive semi-definite. But lambda has a special form, this one. And we know, in addition to that all lambdas are different from 0. We have this three-diagonal matrix, which is, we know it's positive semi-definite, and no lambda vanishes. From this we can conclude that it is in fact positive definite. The argument is a bit subtle. First of all, the determinant of this matrix has a known formula. That lambda is equal to sum of all products of those lambdas, each time one of them taken out. So it is a sum of products lambda 1, lambda I minus 1, lambda I plus 1, lambda n plus 1. Well, don't need product. That's that. That's I. And this is, we know, determinant of a positive semi-definite matrix is itself non-negative. So, so we have two cases. If no lambda vanishes, none, one can vanish. I correct myself, one of them can vanish, we had it. But take first, all of them are different from 0. But this can be expressed as a product of all of them times the sum of the inverses. But we know that this is different from 0. And this is also different from 0. So lambda is positive definite, because then the determinant is positive. That's the only small thing we know. We know that it is positive semi-definite, and the determinant is positive. But that means that all eigenvalues should be positive. They are non-negative. The only possibility would be one of them to be 0, which is not there. But if some of them is 0, then only one term of this sum is remaining. And all others are then then positive. So it is positive definite. Well, this proves the theorem. See, we have heavily relied on the special form of the geometry. It wouldn't be that important if the model itself wouldn't have such a paramount importance as hanging bridges, or even more important, lying cables. There is a cable which is been let down. And cable is almost not elastic. It is quite rigid. So it can be in first approximation taken as a catenary. You will have hundreds of articles dealing with catenary. And besides, it has a nice geometry behind. So, the next theorem, I will just formulate it and have it proved next time, is the, well, yes. I forgot. Before formulating the next theorem, I will come now to the question of 2 dimensions or 3 dimensions, plane and space. What we have proved here? We have proved that the 3-dimensional catenary at any minimum point minimum point is plane. It's a plane configuration, as the minimum is strict. Now, if the minimum is strict in 3 dimensions, it's also strict in 2 dimensions. So we proved the same thing for the plane catenary. But we couldn't do it without this. We had to go into the 3rd dimension to prove this positive semi-definiteness in 2 dimensions. Is quite difficult, and I don't know how to do it.
But it is possible.
I don't know.
You don't.
I made an excursion into the 3rd dimension. I've proved what I need. I didn't cheat you. Yes. So, yeah, and you see how this interplay of dimensions plays a role. And that's the art of mathematicians, that they are able to switch the same object and consider it in different constellations of geometry. The object is the same, it's the catenary. That is one thing to consider it in a plane, and quite another one to consider in the space. This flexibility is a good point with us. So, a theorem. Under the same conditions, we have it here, yes. Theorem. The function V of catenary takes its minimum only once. No further local minima. This solves completely the problem of the catenary in the space, in the 3-dimensional space. Some of this will remain valid in 2 dimensions, but not everything. Look at the following example. Stay in the plane. So you cannot fall down, just stay in the plane. And take this catenary. It's very fine equilibrium. if this is heavy enough. It must, these mass should be much larger than those. It's imaginable. It cannot slip down because this length will not allow it. It would in the space, down there, but not in the plane. So the situation in the plane may allow for more local minima. The simplest of them is this one. It's not physical, but it's simple. Well, I apologize once more for, not for the technical difficulties, but for my mistake in the proof. I promise to give you the correct proof next time. Thank you. I will see you in 1 week. U 9.